Hello, and welcome to another Algebra 2 lesson. This is lesson 6.1. Our objective, graph exponential functions. The parent function for exponential growth is f of x equals b to the x power, where b is greater than 1. When b is greater than 1, the value will increase, so it's a growth function. The graph shows the general shape of an exponential growth function. The x-axis is an asymptote of the graph. An asymptote is a line that a graph approaches more and more closely. An equation of the x-axis can be written y equals 0. Notice the graph rises from left to right, passing through the points 0, 1, and 1b. So if we have a graph of an exponential growth function and we're trying to figure out the equation, this 1b point will be very valuable. When x is 1, whatever y is tells us that base value of our exponential growth function. Notice the domain and range. The domain is all real numbers. We can use all of the x's, and the range, y must be greater than 0. Parent function for exponential decay functions. The function f of x equals b to the x power, where 0 is less than b, which is less than 1, is the parent function for the family of exponential decay functions with base b. The graph shows the general shape of an exponential decay function. Notice the graph falls from left to right, passing through the points 0, 1, and 1b. And the x-axis is the asymptote. So that asymptote is still y equals 0, the x-axis. The domain is all real numbers. The range is y is greater than 0. So if we put these two concepts together, decay and growth from the previous page, f of x equals b to the x, its exponential growth when b is greater than 1, and its exponential decay when b is between 0 and 1. Example 1, graphing exponential growth and decay functions. Tell whether each function represents exponential growth or exponential decay. Then graph the function. Remember, we need to look at the base of the power to decide if it is growth or decay. When b is greater than 1, it's growth. So this one, the b value is 2, so this is exponential growth. And what about this second equation here? Is this growth or decay? This number is between 0 and 1, so this is exponential decay. All right, and then let's work on our graphs. Step 1, identify the value of the base. The base is 2. It's greater than 1, so the function is exponential growth. All right, that's the part we just talked about. Make a table of values. So make a table, plot your points, draw your curve from left to right. So our equation is 2 to the x. So 2 to the negative 2. Remember how to do negative exponents? Well, negative exponents give us reciprocals. So to rewrite this with a positive exponent, we would write it as 1 over 2 to the positive 2 power, and then 2 squared is 4. 2 to the negative 2 power equals 1/4, and that's what's in the table. So do it again with the negative 1. So that'd be 1 over 2 to the positive 1, or 1/2. Anything to the 0 is 1. 2 to the 1 is 2. 2 squared is 4. 2 cubed is 8. So that's how they got these numbers in the table. All right, plot our points, draw your curve from left to right. All right, make your graph. The fractions, we're just going to estimate. Anything to the 0 power is 1. So our exponential growth and exponential decay functions are going to go through that point, 0, 1. That's a really important point for our graphs. And then 1, 2, 2, 4. Goes there. And 3, 8. All right, now draw your curve. Remember, it will not cross the x-axis. It's supposed to approach it, but not touch it. So it'll get really close. And here's an exponential growth function. Growing exponentially. And for B, you're going to do the similar thing. We already decided it's decay. Make a table, plot your points, draw your curve. So I'm going to make a much smaller table. 3 points will do it. Do -2, 0, and 2. Put those into the equation for x and find your y value. So making our table, 1/2 to the -2. Remember, negative exponents give us reciprocals. So we get 2 over 1 squared. That's 4. So that gives us the point -2, 4. Anything to the 0 power is 1. So that gives us the point 0, 1. And then do one more. 1/2 to the +2 power, -2, 0, +2. 1/2 squared. Well, that's 1 squared over 2 squared, or 1/2 times 1/2. Either way. 1/2 times 1/2 is 1/4. So that gives us our third point, 2, 1/4. All right, graph your points, draw your curve. Remember not to cross the x-axis. Y has to, for the range, y has to be greater than 0. And your domain, x is all real numbers. All right, and there's example 1. We graphed an exponential growth and an exponential decay. Remember, when reading a graph, we go from left to right. So exponential growth, when we go from left to right, is going up. Exponential decay, going from left to right, is going down. Exponential models. So real life quantities increase or decrease by a fixed percent each year or some other time period. The amount y of such a quantity after t years can be modeled by one of these equations. Exponential growth model. Y equals a times the quantity 1 plus r to the t power. And exponential decay, y equals a times the quantity 1 minus r to the t power. Note that a is the initial amount. Note that a is the initial amount. R is the percent increase or decrease written as a decimal. The quantity 1 plus r is the growth factor, and 1 minus r is the decay factor. So looking at these two different equations, the only thing that's different is whether we are adding the rate to 1 or we are subtracting it from 1. Adding it's going to make it increase, subtracting it's going to make it decrease. Example 2, solving a real life problem. The value of a car Y in thousands of dollars can be approximated by the model Y equals 25 times 0.85 to the t power, where t is the number of years since the car was new. Part A. Tell whether the model represents exponential growth or exponential decay. So here's the equation they gave us. 0.85. Would I write that as, can I write that as a 1 plus a number or 1 minus a number to get to 0.85? So in other words, is it increasing or decreasing? It's decreasing. If we think about back to our first exponential functions, if that number, this is our b value, if that's less than 1, it's decay. But to find our percent of growth or decay, we want to write it in one of these forms. Identify the annual percent increase or decrease in the value of the car. So we want to use this one for this word problem. This is the formula we are using. Y equals A times 1 minus R to the T power. Our A is 25. But then we need to write 0.85 as 1 minus something. So if you subtract 1 minus 0.85, you will get the number we need. 1 minus 0.85 equals 0.15. Therefore, 1 minus 0.15 will equal 0.85. So if you do 1 minus this number, you will find what you need in your parentheses. Okay, we wrote it in this form. We need to know the percent increase or decrease. So our R, our rate, equals 0.15. But what is that as a percent? Move your decimal 2 places. 15%. And it's a decrease, so we want to label it. We need to estimate T. So when Y equals 8, what is T? So to estimate, eventually, we're going to learn about logarithms, also called logs for short. Once we know logs, which we don't right now, we'll be able to solve this equation for T. But in the meantime, we're just going to have to guess and check. So what if T is 5? When T is 5, put in the equation 25, grab a calculator, do 0.85 to the 5th power, and multiply it by 25. So 25 times 0.85 up to, use a little caret, the little up arrow to get your exponent, type in a 5, see what you get. $11.09. Okay, well, we need to get to 8,000. So that was 11. So 6 probably isn't high enough. Let's try 7. So let's put a 7 in for T. 25 times 0.85 up to the 7th power, 8.01. There it is. There's our 8,000. So our answer is about 7 years. Remember, once we learn logarithms, then we can solve equations for exponents. It's coming up later this chapter. All right, so a car started off with 25,000. It is decreasing in value. We call that depreciation. When we're talking about things losing value, it's depreciating. So it was depreciating 15% or decreasing in value 15% each year. So after 7 years, a car that was worth $25,000 is now only worth about $8,000 7 years later. And that's why I buy used cars instead of new cars, because they depreciate quickly. Example 3, writing an exponential model. In 2000, the world population was about 6.09 billion people. During the next 13 years, the world population increased by about 1.18% each year. Write an exponential growth model giving the population Y in billions, T years after 2000. Estimate the world population in 2005. So one thing at a time. Write an exponential growth model. Okay, our exponential growth model. From the previous page, well, probably 2 pages ago. We're going to use growth, so that's 1 plus R in the parentheses. We need to figure out our starting amount A. There's our A. We need to know our rate. Okay, 1.18% is the rate. So what is that as a decimal? To make a percent sign go away, move 2 decimal places away from the percent sign, further away from it. So it would go 1, 2, fill in a 0. So A is 6.09, R is 0.0118. What else do we need? We've got a value for R, we've got a value for A. Write an exponential growth model giving the population Y after T years. Okay, so we want Y and T to stay Y and T right now. So A is 6.09. And T is our time. And R was 0.0118. There's our equation. That's what it asks for. That's our exponential growth model. So when they say write a model, they're talking about the equation that models the information. Now it's asking estimate the world population in 2005. So what do we use for T for 2005? We're not going to use 2005. T years after 2000. Okay, so T is just the number past 2000. So from 2000 to 2005, that's 5 years. So to estimate it, we're going to put in a 5 for T. Push buttons on our calculator. 1 plus this number is just 1.0118. I can add those together ahead of time. Don't have to, but you can. And then type this in your calculator and see what you get. Then your mark, get set, go. Okay, here's the decimal my calculator gave me. 6.45789. If I round that to 2 decimal places, and I'm choosing 2 decimal places because the number we started with had 2 decimal places, this had 2 decimal places, so we're going to stay consistent with the information they gave us. So it'd be 6.46, don't forget to label it, 6.46 billion. All right, so that would be the estimate for our world population in 2005. Estimate the year when the world population was 7 billion. Okay, so we're going to use our equation we have, the 6.09 times our 1.0118. And we have to try different numbers for T so that we can get 7 billion. So 7 billion was our y. We need different numbers for t. Helps to organize your guesses. We're going to guess and check. It's the only method we have right now until we learn logarithms. So if I try 5, well, 5 was 6.46. We already did that one. So let's count 5 5s. Let's go with 10. If we put in a 10, we do 6.09 times 1.0118 up to, use that little caret up arrow to get your exponent. Put in a 10, what do you get? Let's round it to 2 decimal places. Okay, not there yet. Let's try 15. Type it in, what do you get? All right, I got 7.26, and we want to know when is it about 7 billion. So then you need to try it again. It's got to be in between these two numbers because 7 is in between 6.85 and 7.26. So try 11, 12, 13, 14. We've got to figure out which one of those numbers is closest. Okay, I tried 12 and I got 7.01. So t is 12, approximately. We're estimating. So what year would that be? 12 years after 2000. That'll be right about 2012 when we cross 7 billion people. We're past that now. This is old information. All right, but that's how exponential growth works. And that was only a 1%, a little bit more than a 1% increase. In 12 years, we went from 6 billion to 7 billion. Remember 7 billion? How many zeros is that? There's 7,000. Now that's 7 million. Now that's 7 billion. So 7 billion, that's adding 9 zeros to the end of these numbers. From that decimal place over, it's 9 zeros. So 7 billion is the same as 7 times 10 to the 9th power, to use scientific notation. All right, that's example 3. Example 4. Rewriting an exponential function. The amount y in grams of the radioactive isotope chromium-51 remaining after t days is y equals a times 0.5 to the t over 28 power, where a is the initial amount in grams. What percent of the chromium-51 decays each day? Okay, so we've got this equation. We need it to show percent decay. So we need this equation in that form, 1 minus r to the t power. Right now we have a t over 28. So we have to change this exponent to be just the t. We've got to get rid of that over 28. Write your original function. Use your power of a power property. Power of a power property. So 1 over 28 times t is equal to t over 28. So we're going to pull those two numbers apart so that t can be separated. But this is equivalent to the original equation. Now we can evaluate 0.5 to the 1 over 28 power. And we get 0.9755. Look, now it's just a t. So now we can take this equation and write it as a 1 minus r equation. remember to do 1 minus this number, 0.9755, to find that R number. Because if 1 minus 0.9755 equals 0.0245, then 1 minus 0.0245 has to equal 0.9755. And you can check that on a calculator. All right, so we rewrite it this way, and we see that this is our rate, but we want that in a percent. So the daily decay rate is about 0.0245, or move your decimal place 2 places over towards where the percent sign goes to change it to a percent. So that's 2.45% decay. Okay, that is the decay rate. That's that chromium breaking down. Ooh, here's another good application of exponential functions. Interest, money, compound interest. Consider an initial principal P deposited in an account that pays interest at an annual rate R, expressed as a decimal, compounded n times per year. The amount A in the account after T years is given by this formula. So compounding interest, that's when they actually figure out the interest and deposit it into your account and give you that additional money. Sometimes often it's quarterly. Quarterly would be 4 times a year. Can also be monthly. That would be 12 times a year. So you have to figure out what your N is in these formulas. Finding the balance in an account. You deposit $9,000 in an account that pays 1.46% annual interest. Find the balance after 3 years when the interest is compounded quarterly. All right, write down the formula we need. And we're going to figure out what all these numbers, what variables they represent. Okay, the A is the amount in the account after time has gone by. P is the principal amount. That is the starting amount in the account. So A is the amount after time has gone by. P is your starting balance or amount. Okay, so our P is what we started with. R is the interest rate, but we've got to change that to a decimal. Write that down as a decimal without a percent sign. And it's compounded quarterly. How many quarters of a year are there? 4 quarters in a dollar, 4 quarters of a year. So our N is 4 when it says quarterly, compounded quarterly. Okay, we've got P, we've got R, we've got N. What else do we need? We're finding A. What variable are we missing? Ah, T. T is 3. Okay, put all these in for your variables. Grab a calculator and find your answer. On your mark, get set, go. All right, I'm going to do this in steps. Divided this by 4 and added 1. Four times 3 is 12. Okay, now I can raise this to the 12th power and multiply by 9,000 to get the amount in the account after time has gone by. All right, some word problems will tell you what to round to, what decimal place, some will not, and we stay consistent with the problem. This problem is money. So when you're doing a money problem, we always want to round to 2 decimal places for dollars and cents. So this would be, okay, look at it carefully, round your answer. $9,402.21. That would be the amount in the account after 3 years. Getting 1.46% annual interest compounded quarterly. All right, so choose your formula that applies to the problem. Figure out what you know. Substitute those in. Grab a calculator and figure out your answer. If the variable you're looking for is already by itself, then you just do the arithmetic over here. If the variable's in the middle of the formula somewhere, you're going to have to solve algebraically. So it depends on the problem. If we have to do algebra or just arithmetic to find the value of the missing variable. To solve word problems, choose the correct formula, substitute what you know, then solve for the unknown. Here's all the different formulas we saw today. We started with exponential growth and decay with just a plain exponential function of a base to the x power. It was growth when b is greater than 1, decay when b is between 0 and 1. Then we moved on to these really cool application problems where we have growth, decay, and compound interest. So I didn't label these yet. Help me out. We have this one has a 1 plus r, this one has a 1 minus r, this one has a 1 plus r to the n to the nt. This one's more complicated. A lot more variables in this one. Okay, let's start with this first one. If it has 1 plus r, which one is that? Growth, decay, or compound interest? There it is. That one's growth. So if adding r is growth, subtracting r is the opposite of growth. Decay, that's right. And this last one we just learned, that was our compound interest. So make sure you get those written down. It's a nice summary page. And those are the formulas you need and information you need to help you out with Big Ideas Assignment 6.1. Thanks for watching. Have a great day.